The silicon chip industry stands as one of the most transformative forces in modern history, underpinning the digital revolution that has shaped every facet of contemporary life. At its core, this industry revolves around the design, fabrication, and distribution of integrated circuits, commonly known as chips, that serve as the brains of countless electronic devices. From smartphones and laptops to automobiles, medical equipment, and industrial machinery, silicon chips are the invisible engines driving progress, innovation, and connectivity across the globe. The journey of the silicon chip begins with its namesake element, silicon, a plentiful semiconductor material derived from sand. Silicon's unique properties, its ability to conduct electricity under certain conditions and insulate under others, make it ideal for crafting intricate electronic circuits. The process starts with the purification of silicon, which is melted and formed into large, flawless crystals known as boules. These are sliced into ultra-thin wafers, each serving as the canvas for thousands or even millions of microscopic circuits. The fabrication of a silicon chip is an exercise in precision and complexity. Photolithography, the technique at the heart of chip manufacturing, uses beams of ultraviolet light to etch circuit patterns onto the silicon wafer. Layers of materials, metals, insulators, and semiconductors are deposited and etched away in a painstakingly orchestrated sequence, gradually building up the intricate architecture of transistors, capacitors, and interconnections. Each transistor, a minuscule switch that controls electrical signals, measures just a few nanometers across, smaller than a virus and invisible to all but the most powerful microscopes. As the demand for faster, smaller, and more energy-efficient devices has grown, the silicon chip industry has relentlessly pursued Moore's Law, the observation that the number of transistors on a chip doubles roughly every 2 years, leading to exponential growth in computing power. This relentless miniaturization has driven astonishing advances, enabling smartphones to outperform supercomputers from just a few decades ago. However, as transistors approach atomic dimensions, the industry faces formidable technical and economic challenges, sparking a new era of innovation in materials, architectures, and manufacturing techniques. Central to the industry's evolution are the companies that have defined its landscape. Giants like Intel, TSMC, Taiwan Semiconductor Manufacturing Company, Samsung, and AMD have vied for supremacy, each contributing unique strengths. Intel, long the leader in processor design and manufacturing, pioneered many foundational technologies and set the pace for decades. TSMC, meanwhile, revolutionized the industry with its foundry model, producing chips designed by other companies, a shift that enabled the rise of fabless firms like Qualcomm, NVIDIA, and Apple, who focus on design while outsourcing production. This division of labor catalyzed innovation, allowing designers to push boundaries without the immense capital burden of building fabrication plants. The capital intensity of silicon chip manufacturing is staggering. Building a state-of-the-art fabrication facility, or fab, can cost upwards of $20 billion, with clean rooms, advanced lithography machines, and rigorous quality controls required to achieve defect-free production at nanometer scales. The most advanced fabs rely on extreme ultraviolet, EUV, lithography, a technology so complex that only a handful of companies worldwide can supply the necessary equipment. ASML, a Dutch firm, dominates this niche, supplying EUV machines that cost over $150 million apiece and represent the cutting edge of human engineering. The geographic distribution of the silicon chip industry reflects both historical developments and strategic considerations. Silicon Valley in California earned its name from the early concentration of semiconductor firms, but today, the industry's epicenter has shifted toward East Asia. Taiwan, South Korea, and increasingly China have become dominant players, thanks to massive investments in infrastructure, talent, and research. TSMC and Samsung lead in advanced manufacturing, while China's SMIC, Semiconductor Manufacturing International Corporation, is rapidly catching up, spurred by national ambitions for technological self-sufficiency. This geographic concentration has profound implications for global economics and geopolitics. Chips are not just commercial products, they are strategic assets, critical to national security, economic competitiveness, and technological leadership. Recent years have seen rising tensions between the United States and China, with export controls, investment restrictions, and efforts to reshore manufacturing, reflecting a growing recognition of the chip industry's centrality. The COVID-19 pandemic and subsequent supply chain disruptions further highlighted vulnerabilities, as shortages rippled through industries dependent on reliable chip supplies. Innovation in the silicon chip industry extends far beyond shrinking transistors. New materials, such as silicon carbide and gallium nitride, are being explored for applications where traditional silicon reaches its limits, such as high-power electronics and 5G communications. Chip architectures are evolving as well. Three-dimensional stacking, chiplets, and heterogeneous integration allow designers to combine different types of circuits into single packages, optimizing performance and efficiency. The rise of artificial intelligence and machine learning has spurred specialized chips, so-called AI accelerators, that depart from traditional designs to handle massive parallel computations. The industry's ecosystem is vast and interconnected, encompassing not only manufacturers and designers but also suppliers of raw materials, equipment, software tools, and intellectual property. Electronic Design Automation, EDA. Firms like Synopsys and Cadence provide the software platforms for designing and verifying complex chips, while packaging and testing companies ensure reliability and performance. The interplay among these players is essential, as breakthroughs in one domain often ripple across the entire value chain, enabling new products and markets. Sustainability is an emerging concern for the silicon chip industry, given the enormous energy and water requirements of advanced fabrication. Fabs consume vast amounts of electricity and ultra-pure water, raising questions about environmental impact and resource availability. Leading firms are investing in renewable energy, recycling systems, and process innovations to reduce their ecological footprint, recognizing that long-term viability depends on balancing growth with responsibility. Talent is another critical dimension. The industry relies on a highly skilled workforce: engineers, physicists, chemists, computer scientists, capable of solving problems at the frontiers of science and technology. Education and training pipelines, collaboration with universities, and global mobility are vital to maintaining the flow of expertise. As competition intensifies, attracting and retaining top talent becomes a strategic imperative, influencing decisions on where to locate facilities and invest in research. Looking to the future, the silicon chip industry faces both daunting challenges and unprecedented opportunities. As physical limits to miniaturization loom, researchers are exploring new paradigms: quantum computing, neuromorphic chips inspired by the brain, and even molecular-scale electronics. Each represents a potential leap forward, but also demands breakthroughs in materials, manufacturing, and theory. The transition to post-silicon technologies may be gradual, but its impact could be as profound as the original invention of the integrated circuit. Meanwhile, the societal impact of silicon chips continues to expand. Ubiquitous connectivity, the Internet of Things, autonomous vehicles, and smart cities all depend on ever more capable and efficient chips. Ethical and regulatory questions arise as well: data privacy, security, and the potential for technological unemployment all trace back in part to advances in semiconductor technology. Policymakers, industry leaders, and civil society must grapple with these issues, ensuring that the benefits of progress are widely shared and potential harms mitigated. The economic significance of the silicon chip industry is immense. It drives trillions of dollars in downstream value, from consumer electronics and cloud computing to industrial automation and healthcare. Entire sectors, finance, entertainment, education, have been transformed by the computational power unleashed by chips. Productivity gains, new business models, and global trade patterns all reflect the pervasive influence of semiconductors. Competition within the industry is fierce, with companies racing to outpace rivals in performance, cost, and innovation. Patent portfolios, trade secrets, and standards battles shape the competitive landscape, while mergers and acquisitions continually reshape the roster of key players. Startups and established giants alike vie for leadership in emerging domains, from edge computing to quantum information processing. Government policy plays a significant role in shaping the industry's trajectory. Subsidies, tax incentives, research funding, and export controls all influence where and how chips are made. The United States, European Union, China, and other regions have launched ambitious initiatives to bolster domestic semiconductor capabilities, seeking to secure supply chains and foster innovation. These efforts reflect a growing recognition that leadership in chips equates to leadership in the broader digital economy. The COVID-19 pandemic served as a stark reminder of the industry's centrality and vulnerability. Lockdowns, transportation bottlenecks, and surging demand for electronics led to acute shortages, disrupting automotive production, consumer goods, and even critical infrastructure. Companies and governments responded with efforts to diversify supply chains, increase inventory buffers, and invest in new capacity. The lessons learned are likely to shape industry practices for years to come, emphasizing resilience alongside efficiency. Environmental and social responsibility are increasingly important for the industry's long-term legitimacy and success. Stakeholders, from investors and customers to regulators and advocacy groups, demand transparency, accountability, and progress on issues ranging from carbon emissions to labor practices. Leading firms have embraced sustainability goals, setting targets for renewable energy use, waste reduction, and ethical sourcing of materials. These efforts are not only morally imperative, but also central to maintaining public trust and competitive advantage. The pace of change in the silicon chip industry shows no signs of slowing. Emerging technologies such as 5G, edge computing, and the proliferation of connected devices are driving new requirements for performance, latency, and energy efficiency. Chips are becoming more specialized, tailored to the unique needs of applications ranging from virtual reality to medical diagnostics. The blurring of boundaries between hardware and software is accelerating as co-design enables unprecedented levels of optimization and integration. Collaboration is a hallmark of the industry's success. Alliances among companies, partnerships with universities, and participation in global standards bodies facilitate the exchange of ideas and the diffusion of innovation. Open-source hardware initiatives, such as RISC-V, are democratizing access to chip design, enabling a broader range of participants to contribute and benefit. At the same time, concerns about intellectual property theft and cyber espionage underscore the need for robust protections and international cooperation. The human dimension of the silicon chip industry cannot be overstated. Behind every breakthrough lies the ingenuity, perseverance, and creativity of countless individuals, scientists who unravel the mysteries of materials, engineers who devise new manufacturing processes, designers who envision novel architectures, and workers who bring products to life on the factory floor. Their collective efforts have transformed the world, shrinking distances, amplifying knowledge, and empowering billions. Education and outreach are crucial to sustaining this momentum. Inspiring the next generation of innovators requires not only technical training, but also a sense of purpose and possibility. Outreach programs, mentorship, and inclusive hiring practices can help broaden participation, ensuring that the industry reflects and serves the diversity of society. As technology becomes ever more integral to daily life, fostering public understanding and engagement is equally important. The narrative of the silicon chip industry is one of constant reinvention. From the invention of the transistor at Bell Labs in 1947 through the first integrated circuits of the 1960s to the multi-billion transistor processors of today, each era has brought new challenges and opportunities. Disruptive technologies, shifting market dynamics, and evolving societal needs ensure that the story is far from over. The industry's resilience and adaptability will be tested anew as it navigates the uncertainties and possibilities of the coming decades. In sum, the silicon chip industry embodies the spirit of modernity, an engine of progress, a crucible of innovation, and a linchpin of global society. Its impact extends far beyond the realm of technology, shaping economies, cultures, and the very fabric of human experience. As we look to the future, the challenges are formidable, but so too are the opportunities. With vision, collaboration, and determination, the industry will continue to illuminate the path forward, powering the dreams and aspirations of generations to come.